Hi, good morning, folks. I'm Divya. I'm from Pinterest. Today, we'll be giving a talk on near real-time Galaxy, how we built a system that allows for fast, systematic, and scalable Flink application development at Pinterest. I am one of the tech leads on the stream processing platform. Later in the talk, I'll be joined by Hung. Hung built our CI/CD systems. So, how will this all work out today? We'll start out with the Pinterest architecture and business requirements. We'll figure out what's NRTG, why NRTG was built in the first place, the promise that we deliver upon, which is 3 times faster development over offline, and how we deal with time, operators, metrics, job structure, some examples. And you'll see the onboarding outcomes for some of the things that we've worked on, and then we'll talk about some CI/CD. So the Pinterest architecture in 2019 was a process of evolution. We have our service which does the API layer, and that was publishing a bunch of Kafka messages that were relating to a bunch of our engagement topics and so on. And then we had our source of truth ChartDB that was providing data dumps. This is a simplified architecture. A lot of systems are eliminated from this. But broadly speaking, what you'll see is like a Lambda architecture, and you'll see Batch Galaxy, which does all the heavy lifting. There's millions of dollars of compute going in here. And then you had a very fairly lightweight layer that was just for some fast signals or just very lightweight counts and whatever's required. And the characteristics of the system, it's a reasonable Lambda architecture. It was built over 6 years, over a period of growth for Pinterest. It was suited to the strength of each system. The bulk of the heavy lifting was done by batch, and streaming was done for quick and real-time results. And the weaknesses were that we had to build custom systems to deal with counts and impression deduping, because Pinpin was event by event Kafka. You didn't have a join, you didn't have you didn't have a group by on the stream. There was no notion of event time, and because we didn't have checkpoints, there were drop messages on every restart. No rewind, replay, no way to bootstrap the data. There's some scaling issues that we had to work through, and high QPS was challenging because of cost. So what is Batch Galaxy? So Batch Galaxy is the system that allows teams at Pinterest to write and integration test MapReduce jobs and configure them with a few configs, launch immediately on the MapReduce cluster. It's a dependency injected framework with full local integration test support. You can actually run the MapReduce job locally. And you have lineage tracking, you have a full ecosystem around it, some end-to-end latency tracking, metrics, validations, all sorts of good things that you need in a large-scale system. And the outputs of all these MapReduce jobs, they power Pinterest ranking and recommendations, among other things. And it's a fairly important system. So what happened is that Pinterest business requirements changed. So Pinterest, dealt with a lot of static data, images, but the world's changing, and we are in a world where we have idea pins, we have videos, and we have creators, and those business requirements are new, and those business requirements require changes to the infrastructure. And since Pinterest has been shifting towards multimedia data and creators, something called Pinterest 2.0, we have multi-frame pins now. We have video content in these pins. The creators, they want immediate engagement and immediate feedback on their content. The ranking and distribution teams need to know how content is performing to distribute it. The engagement signals are super critical. They need to scale. Trust and safety needs to operate in this environment. And so that's the changing landscape of our business requirements. And that's what causes NRTG to be built out. So what's NRTG in the first place? NRTG is near real-time Galaxy. From the name, you can think that it's like a streaming analog of the Batch Galaxy. And it follows the same data flow API that's used in Batch. It's same down to a fault, and extends it to streaming and completes the Lambda architecture in a single system. It's built for scale and it's for ease of development. And the promise is if you write an NRTG job, you will get your code right as soon as the integration tests pass. And the only thing that needs to be done is to tune the job for scale. And if the design patterns within the framework will guide you to write jobs that meet our business requirements, they will work fast in production, and they'll have a guaranteed baseline quality and a guaranteed baseline set of metrics, so that if something's going wrong, there's enough visibility and you don't need to, re-instrument every job for all the basics all the time. And the goal is that we want to be able to scale to hundreds of Flink jobs owned by tens of teams that are straightforward to debug, tune, and evolve. And if there are any issues, we should be able to find them immediately. And so before we go forward, this is like a quick intro of what near real-time Galaxy looks like when somebody's writing code for it. What you'll see is a stream join. Just take a quick look at the video. So you'll see that this demo reel, it was built for our internal teams, and I'm just sharing it with you here today. If you just find a way to move next. And so we can continue on why NRTG was built in the first place. We need the same fidelity of building signals in near real time as building signals on batch. They need to be fast. They need monitoring metrics, lineage, end-to-end testing support, completeness in Lambda architecture, and the ability to share code. Single developer experience across real time and batch, and we need speed of execution for our clients. Our client teams are business teams. They are not Flink experts. And we need engagement signals from really high volume Kafka topics. We need to have streaming group by stream joins, and we're building an ecosystem of interdependent stacked streaming jobs. And they need to scale as new signals are added. If there's an incident on one signal, the entire pipeline should not come to a halt. It needs to just continue working with the best available data. And different teams own different jobs. They're just not Flink experts. And so if you're writing a Flink job, I think those who've been in this industry for a bit, they understand that there are some common problems that everybody needs to solve. There needs to be serialization, checkpointing, how you do async RPCs, how you connect to sources, how you connect to sinks, what kind of DAG structures you have, how do you tune parallelism, what kind of operator choices that you get. You have late data, you have error conditions, you have metrics, data bootstrap, Flink job best practices. Streaming is a lot more complex than batch. And we need to take executive decisions on behalf of our client teams. And there are a lot of gotchas that you can hit with the Flink data stream API. I think those who work with the system do understand that. And then our goal is to ease the path to building a Flink job. And I'm going to give you like a brief overview. This is what NRTG looks like at the top level. Like these are all the components. Everything in yellow and the deep blue is infrastructure that is built for our clients. You'll see sources, sinks, core operators, config management, async operations, logging infrastructure, metrics infrastructure, juice dagger ingestion, RPC support with Finagle. All of this is like general streaming infrastructure, and we built it to power the Galaxy frontend. And it's also reusable to the form that we're figuring out how to convert it for general stream processing within the company. And so we'll move forward to the fast, systematic, and scalable promise. How do we get 3 times faster development versus the data stream API? You'll see some of the results. But before we get there, we need to talk a little bit about relational algebra. So if you're familiar with theory, batch is built upon relational algebra, and cascading was our lingua franca for batch for a very long time. Now it's Spark, but it was built on a very batch Galaxy was built by simplifying the operators needed to implement relational algebra to the very minimum, just 3, which is flat map, group by, and outer join. If you implement these 3, you have the capability to completely implement 100% of batch jobs. And it fully supports relational algebra. And that's exactly what Batch Galaxy did. It took these 3 operators, implemented them really, really well, and you have a full setup for batch processing. NRTG takes it up a notch. So it's based upon Flink operator set and simplified down to 8 cases. And it implements temporal relational algebra. Temporal relational algebra is a lot more complex. There are a lot of subtleties with time, subtleties with, how far back you can look, how do you deal with extended aggregations? How do you deal with extended joins? But, after a bit of a careful design, if you come down to 4 into 2 cases, like 4 operators with or without async, you can actually cover the set of all streaming DAGs. Note that these are DAGs, that is acyclic graphs. So if you don't have loops in these sets actually cover all of them. And these cases need to be handled in both processing time and event time. And a big design doc was written, but the end result was that if you look through these operators carefully, it shows that it covers the full operator set, including full scale group bys from t equal to 0 with external state. And it handles the full generality of stream processing. So we wrote it up. And it was not a short job to write up. Like this framework's like easily the largest backend for Galaxy we've written. It was about 36,000 lines of code, 15,000 lines of main source code, 25,000 lines of tests, and 158 files for tests, 149 files for code. We have, the impact of this was pretty huge though. Like an average, really simple Flink job will take about 1,500 lines of code across 20 files. Tests will be 500 lines, but you won't get coverage. And typical NRTG, what we call it as a signal, is only about 300 lines of code with 200 lines of tests, but you get full end-to-end coverage metrics, dev, staging, prod separation. You get the works. And so you get a lot for a lot less. And already the numbers, speak for themselves. And it was not easy to build this as well. So Near Real-Time Galaxy is a full compiler in a certain sense. It starts with the single data flow class right at the top level. And we build the entire compiler stack. So you have a Alexa parser, a parse tree optimizer, you have control flow, opcode generation, you have the full compiler front end, you have a compiler backend. And so the input is a Signal Java class into Near Real-Time Galaxy, what you saw in the video. And the output is a Flink stream graph. And everything in between is our business logic. And you'll see sources, sinks, fundamental operators, use dagger support. Everything gets fit into annotations and how that works out. And we handle a lot of complexity in this area. And we won't have time to cover the architecture for Near Real-Time Galaxy. So I'm going to leave all of these slides as reference slides so that you can take a look at it later. But in general, you can see that we have a Alexa, we have a parser, we have like node representations, we have a control flow, DAG generator, this is the builder for the DAG. Then we have like source representations, transform node representations. We have tons of sources, sinks of various kinds. And then the bottom line is that every single NRTG application will look the same. It will have the same jar, the same dependencies, same operators. And if we verify that the 8 core operators in NRTG are working correctly, we can prove that all of the underlying signals will work correctly, at least at the Flink layer. And if there are any issues, they're only with client code. And so if you look at the sources, like this is like a sample annotation for a source, you'll see some of the config associated with the source. And then you'll see map transforms. They have a single stream in, you have a stream out, and you emit your stream outs as you saw in the video. You have group bys, you have stream joins. A simple look at the stream join, you can see a 4-way stream join here. And then, these are like some of the operators that this compiles down to. So we have something that's like 4 lines of code and it'll compile down to, hundreds to thousands of lines of code, just managing all of the type complexity, data transformations, and so on. We have async transforms, continuous group by cases, which handle a lot of complexity, stream join async cases, advanced stream joins, which handle missing late arriving data. I can't go into the details for all of this, but they're all here. And then you can see there are some client-facing APIs, config issues, things that we work through. You can see that if you want to add a sync or if you want to add multiple syncs, all you need to do is just configure it in the config. So if you're running in dev, just add no syncs. If you're running in staging and prod, you can add as many syncs as are appropriate for the environment you're running in. And you don't need to change any of your code. Your code's working just fine. Only the input sources, the output sources, output syncs, they all change depending on the environment that you're running in. And this is actually pretty powerful because, clients love the feature. So we also had to do a lot of work with the serialization layer. We actually completely reworked serialization to make NRTG work, especially around stream joins. And we support 80 plus types that you can serialize, including immutable types, things that are difficult to serialize with cryo. And you'll see, just as a sample here, you'll see thrift, flat buffers, protobuf, autotuple, JSON, values, Flink tuples, and everything is supported. So our fundamental abstraction is the NRTG tuple, which actually is a TKV tuple. So you have a timestamp, a key, and a value, and can handle any value type that you'll probably throw at it. We also have integration test support, and we spent a lot of time getting that right. So this is a quick recap. All of this got built just to make this thing work. And what's the power of this thing? So if you're going from, a 2-way stream join to 3-way stream join, all you need to do is just add 1 line. And internally, all of the code will just, all of the types, all of the code, it'll just all rework itself to make sure that the 2-way stream join went into a 3-way stream join. Just 1 annotation and you get a lot of power. We have a fully type-safe DAG, so we check that you're not writing DAGs that are like incomplete or that are not syncing into stuff. Or the type checker makes sure that all of the types match across the different nodes. And the serialization layer should just work, but it doesn't. On general, Flink uses cryo. There are things that can go wrong if you're not careful. Schema evolution's been a problem. We've seen a bunch of safe point restore failures if we get things wrong. Type inference has always been an issue because you have to handhold type inference because we've written all of this in Java and type erasure makes it hard. And we are writing second order code. We're writing code for code. And types which look like list of set of T, where T is not known at compile time. It's provided by the user at runtime. It just makes the Flink serialization subsystem and cryo very unhappy, because the type information can't be generated, and we can't really provide a type information that's pretty good. So we just have to completely rework the system to make this work. And so we rewrote serialization. We rewrote it paying attention to performance. It's all binary messages packed tight with message pack. Schema evolution works. Cross type composition works. You can dynamically pick the right serializer for a given type. And we have fully type safe messages inter node. And even things that you can't really serialize well. So if you have like classes that don't have good serializations, for example, immutable list from Guava, we can handle those cases. And on both sides, you'll get an immutable list. And then, you have 80 plus data holders that are supported. And even if you see a type that looks like this, where you have a 4-way tuple with a complex list of a protobuf, thrift, string, JSON, and an object array which could contain an integer long and a double, we'll just get all the types right. We'll serialize it correctly. We'll deserialize it correctly. And it was on the critical path to make stream joins work. RPCs were another big thing that we worked on. We worked on stat support for these RPCs, worked through class loader leaks. We worked through a native JVM deadlock when, thrift was not thread safe. So checkpointing and restore can actually deadlock the job. We worked on RPC back pressure support, when QPS is greater than rate limit. We worked on in-process heal to gracefully retry after a delay. And we used the iterate operator. Many more issues got resolved. And here you're seeing like back pressure triggering from an RPC. So if capacity gets reached, we'll just trigger back pressure. And if you have 500s, the underlying RPC is having trouble, then we'll just hold the message for a bit, and we'll come back and retry later. And you can see this, our in-process heal support working here. And end-to-end integration testing worked out. We stubbed out Kafka topics, bound data to RPC services, injected fake Guava modules, changed the DAG structure. We add and remove syncs with only config changes, dev staging prod differences exist, and we assert on job outputs and metrics. Lots and lots of hoops to make this work well. It took us more than a month, pretty long to actually stabilize this. And we've thought through a ton of ecosystem issues. So how do you choose between processing time and event time? Should all tumbling windows use window smearing? And you'll see what this is. If we have missing or janky timestamps, what can you do? Our watermark assigner will handle it. Do we have S3 based backfill support? Yes. Can we backfill from a batch job? Yes. What happens if our upstream is having issues? We have design pattern recommendations. Do we? And they all work so that it's graceful recovery across the board. What's my data lineage? Can I run multiple signals in a job? All of these things we just thought through, and we worked through this process. And here you'll see window smearing, one of our famous features. You'll see this is the standard tumbling time window on the left. And then we move to a smeared variation where the tumbling time windows semantic is maintained, but the offsets get smeared, so that the underlying RPC services don't get spiky load that's like several times their median. And if you have dirty data like we do, you can have a situation where timestamps are wrong. They can be in the future. And once event time moves into the future, you just have to drop all data. And so we work through a watermark assigner that actually solves that problem for us. It's fairly robust and doesn't require tuning. You don't need to give it a lot of parameters, and it just handles the robustness for you. We have cases where we have stream joins failing because one of the upstream inputs had a problem. Our stream joins always come with an RPC backup. And so, and that's to ensure that our fast signals, they don't wait, and we always have the best available data at all times. So here, the trade-off between event time and processing time, we prefer processing time just to make sure that we are always producing output, even if the upstream is having issues. And you can see that the fallback RPCs kick in as soon as the upstream has issues, and either batch data or previously generated real-time data are used to fill in the stream join and make sure that the stream joins work. And we have these recommendation structures where you can decide how to choose processing time and event time. And so what was the outcome of our onboardings? We got great adoption. And if you're looking at 2020 was when we built out the bulk of the system. And after that, it's been more or less a very smooth growing curve. And raw Flink jobs on the data stream API have settled down to a very, very low onboarding rate. And these are some of our jobs. You can see this job, it's fully unchained, and you'll see this job being built with less than 1000 lines of code, which if you've written large Flink jobs, you'll realize how big of an impact that is. 80% of those 1000 lines was client business logic. There was only 200 lines of structure, and there are 30 plus boxes, 4 stream joins, 1 union, 1 Kafka, KV storage sinks, all of the works. And the entire thing is just one class for the client. And this is the same job, just with full prod optimizations, fully chained. And you can clearly see the sources, how they get joined into 4 stream joins, get union together, and then output. And it's a fully optimized DAG. Here's a different signal. Here you'll see multiple stream joins, multiple RPCs, and that's less than 1000 lines of code, all including all the RPC calls, error handling, everything. And this is the same job structured in. You can see the 2 stream joins and the union at the end. And here's our in-process heal loop, where you can see there are like 2 sets of RPCs that require in-process healing. And whenever there's a 500 that's seen on that service, it just uses the iterate operator to come back and heal it. And it's 300 lines of code for the client, but you get like a job that looks like this, and it's pretty fantastic. So now we'll move, I'll hand off to Hung, and who will walk us through CI/CD, which is the future of the platform. Take it away, Hung.
Now let's look at CI/CD. Xeno CI/CD framework is built to address operation pain points. The first pain point we have is, before production job deployment, repeated job validation are done manually for each landed change by Signal developer. Some steps are listed here. If it is a new use case or it is a big code change, Signal developer also needs to do load testing and chaos testing, and both will require coordination from SRE and platform team member. The second pain point we have is framework changes take too long to roll out. Framework change will affect every application, and it is almost impossible for us to do a validation of the framework change on every application. Such insufficient validation sometimes cause job deployment or runtime issues. Last but not least, CI/CD is always desired. However, there's not much experience shared within the Flink community about how to build a CI/CD experience for streaming applications. Let's look at the overview of Xeno CI/CD. Actually, the idea is pretty straightforward. When there's new artifact build with Bazel in Jenkins job, after PR landed into our Java mono repo, the CI/CD pipeline kicks in. It checks the new artifact and auto-trigger validation for this new artifact. It will launch a validation job to do all kinds of checks. And if the checks pass, it will trigger production deployment of this new artifact. Then the new changes or the new artifact are just in effect in production. So the underlying infrastructures correspondingly are listed at the right-hand side. As you can see, the CI/CD pipeline are executed by Spinnaker, which was open sourced by Netflix. Internally, we use Spinnaker to build CI/CD pipelines for online services. We also use the same infrastructure to build CI/CD for our streaming applications. Hermes is an internal service to do job deployment. It offers UI and also opens the API to do job deployment. Now let's look at the CI/CD pipeline in more details. It is nothing but a series of steps doing some checks and deployment. We call each step a stage. There are multiple stages involved here, and we can classify these stages into 3 categories. The first one is about a trigger. It check artifactory based on some cron rule, and auto trigger next stage for newly detected artifact. The second category is about validation. So we use a validation job to do all the validations. So we stage 1 to stage 7 are all about validation. As you can see, it pretty much cover all the manual efforts that is done by Signal developers, except chaos testing and load testing. So chaos testing and load testing I will talk about more in a moment. And also stage 8 to stage 11 are production job deployment stages related. It checks whether it is a good time to deploy production job. It will stop the existing production job, generate some save point, deploy the new artifact for the production job, and then check the job submission, make sure it launched successfully. Also, we have UIs for the CI/CD pipeline. Hermes, as I mentioned, it's an internal tool. It also displays the CI/CD pipeline. It has information like a trigger history. It has the pipeline operation options like disable, enable, pause, resume existing CI/CD pipeline. Also, we have a Spinnaker UI available. It will show execution detail of each stage. As you can see, the CI/CD pipeline stages are organized as DAG. Actually, it's a linked list. We make it very easy for Signal developer to set up a CI/CD pipeline. So the Signal developer just need to add CI/CD related configs to the existing job deployment config files for staging job and for production job respectively. As you can see, they pretty much just need to copy this config and specify a name. Here we have an example. It's called the Xenon Platform Stability Job, written in NRTG framework. Most other parameters are just auto. We have some good default value for these parameters, and we have a Jenkins job invokes script and tools we built to auto-gen YAML files that are representing the CI/CD pipeline. A CI/CD pipeline YAML file consists of pipeline info, pipeline trigger, over 30 parameters, and 11 pipeline stages. These stages are fixed. We call it a template. Each CI/CD pipeline will have the same stages. The difference is their parameters. Once the CI/CD pipeline YAML file is available, the CI/CD infra will load the CI/CD pipeline YAML, execute the pipeline, and also display the info on the UI I just showed. The CI/CD pipeline actually help us a lot. It help us to do a lot of validation automatically, and especially when we have some platform change we want to roll out. And also, Signal developer no longer needs to do the manual checks, and they can rely on the CI/CD pipeline to check the job health for them. The ongoing and the future work of the CI/CD framework are just the two aspects. The first aspect, we want to add more type of checks in the validation stage of CI/CD pipeline, like chaos testing, load testing, and then perhaps data validation. The second aspect, we want to add global control for all the CI/CD pipelines. For example, we want to pause and resume all pipelines at once. This will be very useful. For example, we have code phrase or we have some incident. We want to control all the pipeline at once. This will make it easier for platform team to operate the CI/CD pipeline at their applications running on our platform. That's it. Now let's move to Q&A.